Welcome to our second lecture in Topic 1, which is an introduction to reinforced concrete design. And in this lecture, we're going to speak about reinforced concrete. Concrete for construction was widely used by the Romans. Although they weren't the first to create concrete, they were definitely the first to use it in the majority of their construction. Its use declined with the fall of the Roman Empire, but concrete was reintroduced into construction in the 18th century. In 1853, Francois Coignet built the first reinforced concrete house. It was a 4-story concrete house reinforced with iron and built as a publicity stunt to promote his cement business. Nowadays, concrete is the single most widely used material in the world, and reinforced concrete is one of the most widely used structural materials. It's quite amazing to see how far we've come. In the next few slides, we will look at some modern examples of reinforced concrete buildings and structures. On this slide, you can see the Marina City in Chicago, built 1964. At the time of its construction, the 2 corn-cob-shaped towers were the tallest buildings in the world that used reinforced concrete. They were also the tallest residential buildings. Habitat 67 Montreal, built in 1967. This Canadian housing complex houses 354 identical prefabricated concrete units, arranged in random combinations, forming 146 residences. The concept was to introduce a new lifestyle to guarantee people privacy, fresh air, and gardens in order to resolve the issues caused by overpopulation in urban areas. And we can also see the iconic Sydney Opera House, 1973. This iconic structure features a modern expressionist design, and the roof is made of precast concrete panels supported by precast concrete ribs. The structural engineer for this building was Peter Rice, and the most prominent engineer in Europe. More notable structures demonstrating the versatility of concrete include Villa Saitan in Kyoto, built in 2006. Although this construction houses 11 units, it is made to give you the feeling of one big house. The curved holes representing roots, trunk, and leaves gives the structure an organic, natural feel. In the middle, we have the Lotus Temple in Delhi, built in 1986. As the name suggests, this temple is a Baha'i house of worship, which design is inspired by the lotus flower. The temple features a dome covered by 27 petals made of white marble. The Lotus Temple has won several awards, not only in architecture but also in religious, artistic, and political fields. And to the right, we have Trump International Hotel and Tower, Chicago, 2009. This 98-story structure reaches a height of 423 meters, including its spire. Its roof topping out at 360 meters. It is the tallest reinforced concrete structure and the 7th tallest structure in the world. The Southern California Gas Company Tower in Los Angeles is a striking 52-story reinforced concrete skyscraper that showcases seismic resistance design, ensuring resilience in earthquake-prone Southern California. The Long Beach Aquarium of the Pacific, one of the largest aquariums in the United States, incorporates reinforced concrete to create massive water-resistant tanks and wave-resistant structures, allowing it to house over 12,000 marine animals in an immersive environment. The Peace and Friendship Stadium in Greece is a multi-purpose indoor arena with a distinctive reinforced concrete dome, designed to withstand seismic activity in the region. Opened in 1985, this stadium has hosted major international sporting events including basketball and volleyball championships, showcasing its durability and engineering excellence. The Water Tower in Savonia, Finland is an impressive reinforced concrete structure designed to endure extreme Nordic weather conditions while providing essential water storage and pressure regulation for the region. The Statfjord Sea offshore oil rig features a massive concrete gravity-based structure, GBS, built to withstand the harsh North Sea environment and capable of storing over 1 million barrels of oil within its reinforced concrete compartments. The cable-stayed bridge over the Tagus River in Portugal, known as the Vasco da Gama Bridge, is one of the longest in Europe, spanning 17.2 kilometers and designed to withstand strong winds and earthquakes. The Arch Bridge in Roche-Bernard, France, gracefully spans the Vilaine River, combining reinforced concrete with an elegant arch design to ensure structural stability while preserving the natural beauty of the region. The Bartlett Dam in the USA is a massive reinforced concrete structure built in 1939 on the Verde River, designed to provide flood control and water storage in the arid regions of Arizona. The Three Gorges Dam in China is the world's largest hydroelectric power station, featuring an enormous reinforced concrete structure that spans over 2.3 kilometers and helps generate power while controlling the river flow. To understand what reinforced concrete is and why it's so popular, let's consider that reinforced concrete consists of concrete and steel reinforcing bars. Let's now see what makes these two materials such a good match. Concrete, as we discussed before, has poor tensile strength, while steel is strong in tension. Both concrete and steel have good compressive strength. However, steel bars tend to buckle under compression. Concrete has fair and steel has good shear strength. Durability and fire resistance of concrete are good, while steel corrodes and rapidly loses strength at high temperatures. Both concrete and steel have similar coefficients of thermal expansion, and as a result, the combination of these two materials to form reinforced concrete does not generate internal thermal stresses due to temperature change. Based on their material properties, steel and concrete are complementary materials. Concrete is a ceramic and therefore has very low tensile strength. In a concrete structural element, this weakness can be eliminated by providing steel bars in tension zones. Concrete is weaker in compression than steel, while steel bars buckle in compression. These weaknesses are eliminated by large concrete sections, which can carry larger forces and are not susceptible to buckling. Concrete provides an alkaline environment to protect the embedded steel from corrosion, which increases the durability of steel, and in addition, concrete provides fire protection to the steel bars. To understand the principle of reinforced concrete, consider a simply supported beam loaded by a uniformly distributed load. Under this load, the top half of the beam will be in compression, while the bottom half of the beam will be in tension. Since concrete is weak in tension, a concrete beam would fail in tension at low loads. To eliminate this weakness, the tension zone is reinforced with steel bars. Steel reinforcing bars are called rebars. Concrete structures are easily reinforced by steel bars to improve their efficiency. In the example of a simply supported beam, the rebars are placed at the underside of the beam where the tensile bending stresses are the largest. Since steel is much stronger in tension than concrete, relatively small areas of steel bars are required. Steel is also ductile, and as a result, reinforcing concrete elements with steel bars increases their ductility, which is important for the design of reinforced concrete structures. In a reinforced concrete element, concrete is in compression, while steel bars are in tension. Such a structure can work together only when there is good connection between the steel and the concrete. This connection is called bond, and it is generated by three mechanisms: chemical adhesion, friction, and mechanical interlock. Between these three actions, chemical adhesion and friction are weak, while the mechanical interlock is strong. Mechanical interaction is generated by manufacturing bars with ribs, as can be seen in the picture on this slide. The strength of bond between a steel bar and concrete is examined using pull-out tests. The specimens used in these tests are concrete blocks with a single embedded bar. During the test, the bar is pulled out of the block and the applied force and produced displacement, called slip, are measured. Bond stress is calculated from the force. The bond stress slip curves are shown in this diagram for the deformed, that means bar with ribs, and smooth round bar. As can be seen in the diagram, adhesion contributes to the bond only at initial stages before any significant slip occurs. Friction contributes to the bond when the bar is being pulled out. Join me for the next part of this introduction to reinforced concrete design when we discuss the Eurocodes.